right, let's go ahead and get started here. I want to introduce myself. I'm Carly Sapola. I'm the Director of Engagement for the American Solar Energy Society. And I'd like to thank you again for joining us on our monthly webinar series. Before we get started, I just want to update you on who and what ASES is and highlight some of our current events and programs. The American Solar Energy Society, otherwise known as ASES, is a 501c3 nonprofit organization that was established in 1954 and advocates for sustainable living and 100% renewable energy by sharing information, events, and resources to cultivate community and power progress. You can join our community at any time at ases.org/join. Webinar registrants get a special 10% off discount on all of our ASES memberships except for life by using promo code webinar. You can also use this on your renewing memberships. If you're expired, you can use the same promo code for 10% off your renewal as well as new memberships. I want to remind everyone we'll be having our 51st annual National Solar Conference, Solar 2022, Energy Transition with Economic Justice in Albuquerque, New Mexico at the University of New Mexico from June 21st to 24th, 2022. The conference will feature a celebration event for the New Mexico Solar Energy Association's 50th anniversary, a tour of the Sandia National Laboratory's solar research facilities, NABCEP registered solar installer workshops, and much more. Not to mention the opening reception on June 21st will feature the father of modern linguistics and most cited scholar in modern history, Noam Chomsky. We'll also have local poets local to the Albuquerque area reciting poems as well on the evening of the opening reception. The conference will also feature keynotes throughout the week. We'll have Michelle Lujan Grisham, the New Mexico governor, Dave Renee, the immediate past president of the International Solar Energy Society, Shalonda Baker with the Department of Energy, Jonathan Nez, president of the Navajo Nation, Ed Mizria, Sandra Breguet, Gigi Goldman, and Hal Aronson. Lots of big names coming. So please do join us at the conference for our special keynote events, as well as all of our amazing technical sessions. All of the sessions will be live streamed for you to watch in real time, and then they'll also be available later in a recorded format for all conference registrants. There'll be a ton of networking opportunities available in the hybrid format, whether you're in person, online, tons of great ways to connect. Early bird discounts on registration are available until March 31st. We're also offering a special JEDI scholarship for young professionals to receive complimentary registration. You can apply by April 15th. We'll also have additional volunteer opportunities available soon. You can learn more about the schedule, pricing, accommodations, and more at ases.org/conference. And the National Solar Tour. I want to remind everyone to please join us by signing up to host a solar site or local solar tour on the 2022 National Solar Tour happening October 1st and 2nd. The sign-up forms are live now. You can get involved and learn more at nationalsolartour.org. We also have our ASES online community that I want to remind you to join in. It's a space for our community to collaborate, share content, information, and network. We have a special Ask a Renewable Energy Expert Forum where we have our technical divisions on call to help answer your questions about anything solar or sustainability related. Be sure to hop on and engage at community.ases.org. All right, thanks so much for taking the time to listen to my ASES updates. I want to note that this webinar will be available in a recorded format soon. I'll follow up with everyone once it is available. I'll ask you all to submit your comments to the chat section and questions to the Q&A section of the Zoom webinar. We'll review and answer all of the questions at the end of the presentation. Now I'd like to introduce you to today's presenters, Julian Wang and Laura Hinkle, speaking on the topic of uncoupling solar light and heat in passive solar design. Julian Wang, PhD, is an associate professor in architectural engineering and director of ArchiLambda Lab at Pennsylvania State University. He also chairs the ASES Solar Buildings Technical Division. He researches interdisciplinary applications of building science and sustainable, healthy, and interactive building environments. His research projects have been supported by NSF, EPA, USDA, DOE, and NIST. He is also a recipient of the National Science Foundation's Career Award and Illuminating Engineering Society Richard Kelly Award. Laura Hinkle is a second-year PhD candidate at the Architectural Engineering Department at Penn State University. She previously earned her Bachelor and Master of Architectural Engineering at Penn State with a focus in building, lighting, and electrical systems. Laura is co-advised by Dr. Julian Wang, and her research interests include building envelopes, low-energy buildings, and applications of data science to building design. With that, I will let Laura and Julian take it away.
Thank you. So let me share my screen. All right. Okay. So hi, everyone. So you see my screen? Okay.
Yes.
All right. Yeah. So before we entering today's topic, I just want to bring something. Probably you've seen this kind of solar film or called solar heat control film from. You can purchase that from Home Depot or Lowe's or some online stores. You can get this. The function of this kind of a solar heat control film is to reject heat, the solar heat. So from outside, it looks like a metallic material, and it is. And from outside, you could see after installation, you can see something more specular after installing this kind of a film compared with the ones without this kind of film. And from inside, we can also see the significant difference about the incident solar light from heat and light perspective. So we do have this kind of a product and I measure that in our lab. It can reject solar radiation about 70%, more than 70%. So it does work for rejecting solar heat. But meanwhile, I also want to indicate it's not only about the solar heat, right? When you see this, especially the third image from inside of the building, we could see the solar light is, solar radiation is reduced, not only solar heat, right? Heat and light. So if we look at the solar radiation, the solar heat comes from both visible part and infrared part. Infrared is about 53%. So the visible part about 50%. So when we control solar heat, solar light or visible light will be controlled as well. That's mostly happened for this kind of films or products. So that's one aspect I want to mention. And the second one is it seems really good for retrofitting buildings with some solar control abilities. So as a building engineer, so I thought this not hard to be installed. So I purchased the product from, I think from Home Depot or from Lowe's, I don't remember. So I got that. It looks not hard. So I use that and apply to my windows on the facing west on that part of my home. But unfortunately, so my result is not that well. So you could see the films are wrinkled and got some issues. So depending on the products, some of them more fragile. So some of them probably good, but anyway, so we can apply this kind of thing for passive solar design, but depending on the products and depending on their properties. And of course, we need to follow the instruction probably clearly to avoid this kind of failure. All right, so just to give you some information about this, and this will be the central topic we will handle today. We will have four aspects or contents talking about this. The first one, I want to just re-emphasize the solar light and the heat, the purposes of these two portions in passive solar design. And then we will move to the spectral selective windows, which have been developed in the past few years to address this kind of uncoupling needs. And then we'll also mention something about dynamic window technologies. So again, here is still about passive. When we mention passive solar design, the passive could be dynamic. The passive in this scope is the technology we directly use solar radiation, not converted to electricity using photovoltaic. So that's the kind of the scope in this presentation. So even for the dynamic window technologies and not for converting solar energy to electricity, it's still about the solar radiation thermal energy utilization in a dynamic fashion. And the last part is about the supporting tools which we can use for architects or for homeowners, can use that to make some window and transparent facade selections. All right, so let's start. So for the purpose of a solar light, light and heat, first let's see this solar radiation again. The visible light, it includes the three parts in general: the UV part, visible part, and the infrared part. The visible part, the x-axis is wavelength, so nanometer. So from 380 to 780 nanometers is a visible region. But not, I mean, the visible light is not, I mean, for each wavelength, and they are not equivalent contribute to human eye sensitivity. So we do have our sensitivity curve. We call that photopic curve, or photopic sensitivity curve, or photopic vision. So our human eyes are more sensitive to 555 to that specific wavelength, and not that sensitive to the other parts, blue and red. So in other words, the visible light, the central part, like green part, will be more, well, kind of a brighter compared with the other portions. So we call that visible light or photopic light because it's mainly for indoor human occupants. And another portion is infrared. So the solar infrared from 780 to 2500 nanometers, which is about 53% of solar radiation. But again, for solar heat, it's not only solar infrared. The visible part also contains the photon energy in visible portion can be eventually converted to solar thermal, to the thermal energy as well. All right. So for these two portions, solar light and the solar heat, for light part, what we call the photopic light or visible light of solar, the purpose of this in passive solar design, I think is straightforward. We use that for daylighting, for view through the windows, and also we understand the visible light or daylight can bring some benefits to well-being and productivity, etc. Okay, for the heat of solar will be a little bit complicated because mostly we will handle the different seasons because the solar heat we want in summer. We want solar heat against in winter, and we want to reject that in summer. So that's really common. You see the seasonal design about overhang, the shading system. We try to play with the solar angles in different seasons. We also have some elements design which can utilize the solar radiation, like a trombe wall, solar chimney, and we use that to drive natural ventilation or to use the thermal energy stored from solar. Okay, so if we get back to this solar distribution, so we mentioned that the solar light, this is the visible part from 380 to 780. The solar infrared is just a portion of the solar heat. Solar heat does include the light portion. Okay, the solar heat does include the light portion. So controlling the solar heat will affect the solar light. So that's kind of the situation we often face when we select windows or any transparent facade materials or facade panels for passive design for the buildings. In windows or in the glazing area, we normally have two parameters to illustrate this. For the general solar heat, we use a solar heat gain coefficient, which is from 300 to 2500 nanometers. So it's a broadband, a whole or the full spectrum of the solar radiation. And we use the visible transmittance, TVs or VT, to calculate, to report the window visible transmittance. So you often see that if you purchase new windows, you will see kind of a label. It has these two parameters, ASES and the visible transmittance, maybe percentage or point something, like 0.7 or 0.6. And normally you will also have another part, it's a U value, which is not discussed in this one. But anyway, so SGC visible transmittance are required to be reported for window products or transparent panel products for building use. There is another indicator or parameter, which is often ignored or less known than these two parameters, which is called light to solar gain, or LSG. So LSG is the ratio between visible transmittance and the solar heat gain coefficient. So it's a ratio. So when they are same, the LSG is 1. So if we put all the window products into a diagram, in this diagram, X is SGC from 0 to 1. 0 means 0 solar heat gain is transmitted, and 1 means all the solar heat gain is transmitted. And visible transmittance, I think you know this kind of, I mean, you know the meaning about that, from 0 to 1, or from 0 to 100%. And all the points in this diagram represents, I mean, each point represents one product. So we put all the product information from a database from the United States National Financial Rating Council. So they got all the products there. So we just extract all the data about the products and put here. So we can find, this is the central line, the LSG equals 1. So that means when we control, I mean, this SGC is equal to the visible transmittance. But there is another thing there are some other things we can find from this diagram. The first thing is they are kind of correlated. The SGC and the visible transmittance are kind of correlated, linear correlated and positively correlated. When we have a high SGC, we have high visible transmittance. That's something this diagram tells us. And they also have some information that some area, you can see they have forbidden zone or color zone, neutral zone. So these diagrams gave us information telling us the window products or glazing products in our real world, they do have some restrictions, or they do have some limitations. When you design something, you cannot freely put numbers there. You put extremely high visible transmittance, extremely low solar heat gain coefficient. That's not possible in this way, or that's theoretically not possible, or theoretically not possible, or we don't have products there. So this gives us some design restrictions, and how we got this? We got from 8,000 different manufacturer product lines and 550 products here. So I think it's a good representation of the current state of the art for our transparent glazing or facade panel products. So using this, we set up kind of the regression models. So the SGC is correlated to visible transmittance and emissivity. So we set up kind of a limitation, a function, and we use this function for students for them to do some simulation, energy analysis, or passive design to give some design restrictions. So we use that for energy delighting performance simulation. So if you're interested in this, we do have 2 papers published about that, and share the statistical models about this. So using that will be more real to link to the real building window products or facade, like curtain walls or something. And here I also want to make some notes about this. So here you can find we do have a forbidden zone. So this forbidden zone, that means something theoretically we cannot design or create the window products with extremely high visible transmittance and extremely low SGC. So we don't have such products. So now I will just call and ask Laura can give a really quick introduction why we do have this kind of forbidden zone. So Laura, could you?
Yeah. Mm-hmm. So we have the forbidden zone on the graph because the solar heat gain coefficient spectral range includes the visible region. So we showed that in the previous slides. So just for an example, if we tried to design, so yeah, there you can see that the visible region is within the spectral range that's included to calculate the solar heat gain coefficient. So then looking back on the graph that we have the forbidden zone, if we try to design something, for example, with 80% visible transmittance, it's not possible to achieve less than about 0.1 solar heat gain coefficient if you're looking at that line, because the visible region, which we said is about 500 to 600 nanometers, occupies more than 10% of the overall solar radiation, which is used to calculate the solar heat gain coefficient. And this also has to do with the fact that the solar radiation's peak is also about 500 nanometers. So going off this example, if we wanted to design with 80% visible transmittance, the solar heat gain coefficient would have to be greater than 0.1 due to how they're inherently related.
Great, thanks. So we do have this kind of a limitation and put that into our courses or student projects. So when student design something like passive solar house or commercial buildings, when they try to select curtain walls or building windows, we ask them to check the limitations in the real world. You cannot freely design the parameters because they have some theoretical limitations or intrinsic limitations. So in general, when we have this kind of, these are about the products, the real products, the window products. So when we do some selection for houses, for residential or commercial buildings, in general, we want high and stable visible transmittance. We want very good, clear, and stable visible transmittance. So let's see, it's higher than 50%. We want some window products in this range. But for the cold climates, we want, in this kind of visible transmittance situation, we want a relatively higher solar heat gains. We want more heat in this part. So LSG lower than 1 will be the products we want to select for cold climates. And on the contrary, for hot climates, we want a relatively lower solar infrared or solar heat in these products or the properties of the products. So LSG higher than 2 will be the part we are looking for. However, if we look at the points here, we do have, a bunch of products in the market. In the market, they provide the good the visible transmittance and SGC for cold climates. So they are pretty good. We have lots of options. Unfortunately, we don't have lots of options in the hot climates. So you may have experience if you go to like Florida or Texas. Very common you see they use a low emissivity coating on the high-rise building. So from outside, it's really specular and reflective. And the inside is, yeah, of course, because they want to reject the solar infrared, the solar heat. But the inside, you could see the transmittance is also strongly reduced, maybe only 10%, 50%, less than 20%. So we understand the daylighting is beneficial. If we add the solar light, if we can add pure visible light into the room, it can still bring some benefits like the daylighting benefits or well-being, and also you see it outside clearly. So that's this is the part our group is trying to explore. We want to make more available technologies in this zone. We have high transparency windows, but meanwhile we can control the solar light, we control the solar heat as much as possible. So this is the part we really want to control, really want to uncouple the light and the heat. And on the other hand, if we are talking about mixed climates, so we also want this kind of two properties can be switchable. So they can switch from this situation to another situation. So that brings us another trajectory is dynamic fashion. Okay. So based on that, we do have developed the idealized window concept, which is about this. The diagram shows we want control, so we always want 100% visible transmittance transmitted from outside to inside. But the solar infrared, we want 100% rejected in summer and accepted in winter. So that's the idealized concept model for the windows. So there are multiple ways to do this. I mean, we cannot achieve this. It's an idealized situation, but we could move step forward toward this kind of goal. So one way to do this is a spectrally selective windows or spectrally selective technology, which is defined by Lawrence Berkeley National Lab. Spectrally selective windows permit some portions of a solar spectrum to enter a building while blocking others. So mostly these high performance glazing materials admit as much daylight as possible while preventing transmission as much solar heat as possible. So for this solar radiation distribution, you can see, if you see this closely, you can find there is a curve, which is idealized transmittance curve. We want infrared to be rejected, and we want the visible transmittance can be transmitted. So to block this infrared, we have two ways. We can do selective reflection or selective absorption. As long as we can control not so much transmitted, we're fine. Okay, so in our group, we work with mature scientists working with some nanoparticles, metallic nanoparticles. They do have very unique phenomena under solar light. So they can, I mean, the solar light can activate a certain wavelength of solar light can activate a plasmonic resonance for the electron system of these nanoparticles. So simply, simply speaking, under certain wavelength solar radiation, these nanoparticles have some specific light to heat conversion or absorption or just the thermal and optical behaviors. They have special thermal and optical behaviors under specific wavelength of solar light. So there are two major effects. One is a spectral selective effect. We can control the size of the nanoparticles or the shape of that, and then we can tune the absorptance or the transmittance of these nanoparticles. So here's an example. You can see if we change the size of that, they are changing. I mean, the spectral feature about the transmittance are changing. And we can also get strong near infrared absorption based on this, on the design. Not only size, we can also change the shape. It could be just a particle or some wires or some other shapes. So they can have different features, the spectral features. And another effect is called photothermal effect. When the light is absorbed, they convert it to thermal energy. They do have some unique features, like they only happened on the local surface and then released to outside. So it's kind of a semi-directed thermal transfer. We already published a paper talking about that. So today we don't have time to mention about this kind of thing, but they do have some unique surface heating feature which cannot be explained or resolved by current conventional heat transfer model or the macro scale heat transfer model. And this kind of light to heat conversion has been used in medical areas for tumor, in the cancer area or cancer treatment area, or it has already been used for solar steam to generate steam for electricity or some other things. Okay, so we work with the mature scientists on this kind of thing and try to apply this to have really strong selective on solar infrared. And then we have some samples. We use iron oxide shelled with copper, sulfur. It's just nanoparticles, and we get small coating and a thin film, and apply this thin film on the window surface. And we measure the light to heat conversion and also spectral situation, and measure the optical features, mechanical features. So this is just a very brief result of what we get for one sample of this. The visible transmittance can be designed with 70% high, more than 70%. The near infrared blockage can be higher than 65%. So eventually, if you can recall, we talked about the LSG. So we try to bring the point to this circle. So we try to expand the production lines or technology availability to this category because we thought it's kind of less in the market. Okay, and we also make some energy simulation analysis to see whether this kind of thing can really change something for the building energy. So we apply this into single pane windows under solar radiation. Winter energy saving potential can be 16 to 20% in the different areas. We have 4 climate zones. So we use that as a case study. And it appears very close to the thermal performance of double pane windows with the low emissivity coating. So there's some information here. If you're interested, you can search our paper. We do have details talking about the benefits using such a spectral selective windows, how much we could save from there. All right, so we already finished the spectrally. So why we need to uncouple light and heat. And then we talked about some works we did with the material scientists for spectrally selective methods. So now we want to talk about something about dynamic, how to make the switchable, the 2 circles. In summer and in winter, we want have some switchable feature for our building facade. So I will pass it to Laura. You could briefly introduce this part.
Yeah, so yeah, like Julian was saying, we're going to extend some of the ideas that we talked about with the spectrally selective glazing and trying to make it into a dynamic glazing technology. So there's many different dynamic glazing technologies for different purposes. The first 2 on the left, you'll see electrochromic glazing and thermochromic glazing, which are both focused on controlling the solar heat gain coefficient that we've been talking about, being able to modulate it based on either the applied voltage in terms of electrochromic or the window surface temperature in terms of the thermochromic glazing. There's also some other technologies that exist, like the SPD glazing on the right, which is mainly focused on controlling privacy. But it still follows the same idea where it's being controlled by an applied voltage. So the goal here is still that we want to be able to switch between the different states. Yeah, so we'll go into some of the advanced technologies. So in this chart, we can see that there's a couple of the state of the art plotting their range, and you can see there's still a fairly linear relationship between solar heat gain coefficient and visible transmittance. Whereas on the right, you can see this graph that we showed earlier where we plotted all of the different technologies. And we can see that solar light and heat are still highly coupled, like we've been talking. And the goal of our lab is that we want to be able to go between these blue and orange circles. So keeping a very high, stable, visible transmittance, being able to modulate the solar heat gain coefficient on a seasonal basis. So in our lab, we've explored and developed preliminary designs for the dynamic fashion of spectral selective glazing. The top one image is the plasmonic nanoparticles, which have tunable spectral features to be designed to independently reflect or absorb the solar infrared, which we were talking about. The bottom one is a different type of technology, which is a temperature-driven structure to switch between high and low solar NIR transmissive layers. And then another approach on the right that we've experimented with is a reversible window, which allows us to take the NIR radiation and release it to the either outdoor or indoor, depending on the season. So these are some of the approaches that we've been experimenting with and developing designs for and testing, simulating to try to get that high, stable, visible transmittance, but changeable solar heat gain coefficient. So with these tools that these technologies that we've been working on, it's really nice for us to have different tools so that we can test and simulate before necessarily being able to model, have it in the field. So some of the tools that we use are from the Lawrence Berkeley National Lab. And basically we model the systems layer by layer. If we're working with just the window glass, we usually start in optics, and you can see that that's the expanded window on the right. And it's just showing the reflectance and the transmission for the glass that's currently selected. But yeah, then we want to model other parts of the window, like the frame, and ultimately put it all together into a system, include shades, the frame, everything about it, and which is shown in the middle we usually use Window. But then there's other software at the bottom that's available to other types of designers like consultants and things like that. Because we want to design at the component level a lot of times in research, but then ultimately capture the whole building energy savings and get the whole picture. So one of the tools that we use a lot to try to model and simulate these new ideas that we have is using parametric energy simulation methods in Energy Plus. Basically, we have a bunch of different sensors or measurements like temperature and humidity that we take in from the simulation and then develop some sort of relation or logic to try to control whatever aspect of the window or glass that we're interested in. And there's an example at the bottom, some logic that's based on the outdoor air temperature. So just switching between different construction states. And Energy Plus has really expanded its capabilities so that we can test these different technologies and also develop control algorithms and see what the potential energy savings are.
All right, great. Thanks, Laura. So I will take from here. So in our lab, we also work with some other things we thought will be helpful for designers or architects working with a solar system. So as we know, we talked about something about uncoupling solar light, solar heat. The solar infrared or near infrared is a major part. But unfortunately, most of our weather file, or if you got data from weather station close to your city, you don't have the solar spectral details. We just have one number about solar radiation. Like we know it's outside right now in our city, probably it's about 600 watts per square meter solar radiation. We don't know how much for visible. We don't know how much for infrared. We roughly know like 50%, 50%. But as more uncoupling technologies appear and more fine-tunable materials are available, we should know. We should know the spectral details accurately. So to get that, we can using some expensive the parameter, the spectral radiometer to get the spectral information. But we thought it's a little bit complicated. Why not using the weather file and try to using some other things to achieve this? So one way we have been working on is try to use the general or typical weather file with broadband solar radiation data. But meanwhile, we extract some useful information from the weather file or from the general weather station, like dew point temperature, relative humidity, outside temperature, wind, cloud installation. We try to put all this data there, and then using some machine learning algorithms. Here is the clustering modeling methods. And then we can decompose the broadband solar data into two parts. So you could still do some simulation in Revit or SketchUp for passive design, and you can get solar radiation. Now you could use some files like this to get the surface. How much is visible solar radiation real in the solar radiation on the surface, or from the incident perspective, and how much is the real part about the near infrared? So I think this is the way it gave more information for designers or homeowners or building owners to understand available sources, and they could use. This is one of the, we try to make this public on our website, and people can use that freely. And you use this kind of a tool. This kind of a tool can process existing profile, existing weather file with this two pieces information. Another part you can also we also understand under different window situations, people may have different thermal feelings. The transmitted thermal part transmitted light can be in different spectral situations. They may have different effects on human thermal feelings because our skin has a specific absorptive, spectral absorption. So some portions are more important to us, can give us high thermal feelings, and some of them are not. So we try to design, based on the existing model, we try to design a new model to add the window spectral into that model and then predict how much the solar can bring into the user thermal effects. So we call that thermal effect index. So hopefully in the future, when you have the label on the building window products, it's not only about U factor, ASES visible transmittance, you could also have something about thermal effect index. So give more information for the designers or homeowners when they make the selection. So that's also one effort of our group. All right, I think we can wrap up. So with the emerging material glazing system development, uncoupling solar light and heat becomes available, which can achieve building energy savings, the lighting benefits, and also good windows view. Of course, they will also bring some thermal effects to the users near window zones. So that's pretty much about the information today we want to introduce. This is the funding source for our project from National Science Foundation and the United States Department of Agriculture. All right, great, thank you. So now we may answer some questions.
Yeah, perfect. Yeah, we've got one in here from Debbie Coleman. Interesting about the properties of single glazing with the films that bring the performance close to that of double pane windows. Does the coating also affect the R value / U value of the single pane glass?
Yeah, good point, Debbie. So unfortunately, we cannot. So this is the only thin film. So it does not have strong insulation. Very thin, like a 100 nanometer thickness. So it does not provide any insulating abilities. But our comparison is under solar radiation. If we do have a solar radiation, bring that into the loop, it does do some. It does improve the thermal performance of the windows. So we only can compare to the double pane windows under general solar radiation situation.
And I know you answered this one, but just so we can say it out loud, we got a question from John Richter. High temperatures reduce the efficiency and output of PV modules. Could a spectrally selective screen reduce the infrared incident light and hence the temperature without reducing the visible light and hence PV production?
Yeah, so I understand the temperature increase, the PV efficiency drops. So that's kind of the big issue in the photovoltaic areas. And spectrally selective materials do have that ability to uncouple that. But unfortunately, we have less materials have selective reflection function or reflection features compared with the ones to have a selective absorption. So far to reflect that, it's still more about like specular, something like a low emissivity coating. So specular materials, they can reflect, but that's hard to control. Less material options compared with the ones to have a selective absorption. So the products we are introducing or the materials we're introducing is still spectral absorptive. We don't have efficiency of PV, that issue. So we just need to work with the thermal energy stored there.
And another one from John Richter. Do you have any window companies interested in using these products that we're talking about?
Yeah, so this is still very early lab stage. We do have some discussions with window companies. So, but I think it's still, I don't want to say far, but still have several years to go to there. but we do see some. We had some discussions with the window manufacturers to see how we can apply this kind of film to the industry. Yeah.
Awesome. And we've got one from Kirby in the chat. With the window that can pivot inside to outside, have you considered the impact on infiltration?
Oh, that's really strong, really good point. That's a strong question we got from reviewer as well. So that's a big part, of course. I do have some discussions with window companies. If we want really have 360 rotation about windows, what should we do? So I have different feedback. When we talk to the European window companies, they said it's not complicated. As long as the hardware, if the technology is worth to do, the hardware can do some ways like that, not complicated. And in the United States, it's hard because most of our windows are fixed or double hung system, they're kind of fixed. But in Europe, they do have a reversible windows. I mean, it's not for energy saving purpose. It's for the cleaning purpose. So they want to flip and then clean the windows. So we thought as long as we can demonstrate this kind of technology can really save building energy, we probably can pursue something to do. So infiltration can be addressed if we design or engineer some hardware to complement this technology.
And a question in the Q&A from Robert Large. I have been following smart windows for years. Cost of dynamic windows for our attached sunroom has been a barrier. Your thoughts on heliotropes technologies?
Oh, I'm sorry, I don't know the heliotropes technology. So, but in general, I could have some comments about dynamic windows. It's true. So dynamic windows still have the cost benefits issue. So like and not only about technologies, some maintenance operation also have the issues because we need additional hardware to do that. So that's also one thing we try to resolve or address. We want to bring the passive way and not activated by electricity or converted to electricity in that type or in that trajectory. We just want to using some passive way and maybe some dynamic features driven by temperature, like Laura mentioned, driven by temperature, some blinds or some pieces, they can be changed their shapes and passively and automatically respond to the need to the solar and outdoor situations. So that's the goal for our group. So I agree with this statement. That's also something we want to compete to reduce to change the fashion of smart windows.
Great. And here's another good question, somewhat related. How do the spectral properties degrade over time?
Yeah, okay. Yeah, this is also a good question. So we have not tested yet. So we don't know the degradation issue. But from the materials we're using, so we use the iron oxide. Iron oxide have been used, but not nanoparticles level, just the regular size. I mean, the iron oxide have been used for glazing, for glass engineer. They have been used and kind of durable. For this one, we believe it's so. I think it is also kind of linked to the previous question that people. We have people talking ask the question about the PV efficiency. I said the spectral selective reflection, less materials compared with that. To achieve reflective, is still now is kind of the specular surface or very smooth surface is still required. So for that kind of technology, I think durability could be an issue if you have dust, to have some other maintenance issues, that the degradation issue will be more serious. Compared with that track, the one we are presenting is more related to absorptive So even though the surface is not smooth, we can still have pretty nice absorption. So I think theoretically, we see this one is more durable than those reflective materials, but we have not tested yet. We will do that probably next 1 or 2 years for the durability testing.
Great. And then question from Frank Kelly: isn't shading a window in the summer the best option for lowering SHG until this technology is available?
It is. Yeah, that's good question, right? So shading is still the best way to do, and it's passive. So the architects always have the chance to design nice shading geometry or something to responding to different seasons.
Great. And then we've got one in the chat from Michael Lipkin. Wouldn't the ability to tilt windows according to seasons allow a broader selection of window glazing? I think this is because light arriving perpendicular to the plane of the window is maximally transmitted by avoiding speculation reflection.
So can I see the question? I didn't see the question.
It's in the chat. If you scroll up a little bit, I can repost it from Michael here. Should be the newest chat.
The tilt windows, according to season, allow broader selection for window glazing. Yeah, that's a good question. I am not sure. I think the tilt window should have more. Yeah, the tilt window should have more. I mean, it should be more sensitive to the solar radiation because you will get perpendicular, like what you said, the normal direction solar radiation. So if you play with that kind of strong solar radiation, we have more opportunities to design the smart or passive design. Is that the question you're asking, Michael?
Sounds about right. Great. Well, those are all the questions. There was a comment from Michael that I thought was interesting, that there are scientists studying how window and like how bird collisions and windows, that there's studies going on to find coding and patterns that help birds avoid hitting windows during high-speed flying. And I wonder how those patterns are making effect into the designs that you guys are working on.
Wow, that's a tough one. We have not considered that yet. I don't know. The only thing I know, so we had a project a few years ago, international project. Is the window has kind of the color, a specific color, and during the night, under luminaire, I mean the artificial lighting, outdoor decoration, artificial lighting, it does appear bluish and does attract lots of birds, and eventually another day some birds died on the ground. So that's the only situation we play with. We had something with the birds. Well, so I don't know, during the daytime what should we work with them? I mean, how we should work with the birds.
Mm-hmm.
Interesting question though.
Yeah, very interesting. Well, great. It looks like those are all the questions coming in. Julian, are you okay with me sharing your contact info as well as Laura's and the follow-up email to registrants in case folks have any other questions that come up?
Yeah, sure, of course.
Okay, perfect. Well, thank you guys so much for coming on our webinar this month. Amazing March webinar on passive solar design. Do either of you have any final comments before we wrap up?
I think we're good.
Okay, great. Perfect. Thanks. Thank you all so much. Thanks to everyone who joined us today. We'll see you next month. Have a great day.
Thank you, everyone.
Thank you.